Hi, welcome back. Let's talk about atomic weights. So, we've talked about the fact that atoms have different isotopes. So, for instance, chlorine has two isotopes. There is a chlorine 35 and there is a chlorine 37. And it has other isotopes, but mainly these are the two. And 75% of chlorine atoms are chlorine 35, and about 25% are chlorine 37. And what we're going to do is we're going to talk about the atomic weight. The atomic weight, or the atomic mass, is sort of the average mass of all the isotopes. So it's the average mass of all the isotopes of an element. And you might just say, well, if it's an average, right, we just add them up and divide by how many there are. But we have to weight our average. So it's the weighted average mass. And the reason we have to weight it is that chlorine, it's not 50-50 which one you get, right? So if you had 100 chlorine atoms, 75 of them would be chlorine 35, and only 25 of them would be chlorine 37. So if you just split the difference in average, added it up, divided by 2, and got 36, you would actually be off because more likely you're going to pick out a chlorine 35. So we have to account for that. So how are we going to do that? Well, it turns out that, so this is the average mass. So I'm going to write average mass off to the side. And we have to weight our masses. And here's the plan. So what we're going to do is we're going to take the weight of each isotope and we're going to multiply it by the percentage and just add it all up. And that gives us the average atomic mass, or the atomic weight. So what's the weight of chlorine 35? So chlorine 35, this guy over here, right, has got 17 protons. We know that because this number down here is the atomic number, and it's got 35 protons and neutrons. And so if it's got 35 protons and neutrons, and if only 17 are protons, we know that 18 have to be neutrons. Why do we know that? Well, 18 and 17 add to 35, or if you prefer, 35 protons and neutrons minus the 17 protons gives us 18 neutrons. How heavy is this? Well, it depends on how much effort you're wanting to put into this. And so I would say for this class, we can just assume the weight of a proton is 1 atomic mass units, and we can assume the weight of a neutron is 1 atomic mass units, and we can just essentially add that up. So we got 17 ones and 18 ones, so that gives us 35 ones. So we have a mass of 35 atomic mass units. That's not quite right, actually, for technical reasons. When these nuclei come together, and when these protons and neutrons come together and form a nuclei, there's actually a slight change in mass, and the protons and neutrons don't quite weigh 1 atomic mass units. So if you look in the book, they'll probably tell you the actual mass of the nuclei. But we can just go ahead and just pretend that everything's a whole number, and chlorine 35 weighs 35 atomic mass units. And we can also guess that if we got 37 protons and neutrons, then if each one weighs 1 atomic mass unit, then the whole thing's going to weigh 37 atomic mass units. So here's how we're going to form the average mass. What we're going to do is we're going to take the percentage of each isotope, and we're going to multiply by the mass of the isotope, and we're just going to keep adding that up. So if we've got two things, we just take the percentage of the second isotope and the mass of the isotope, and if there's three things, right, we do it a third time, and that gives us the average mass. So the atomic weight, the average molar mass, whatever you want to call it, I suppose is totally fine. If there's two things, of course, you know they have to add up to 100. So sometimes you just get the one percentage, and you're just assumed that you can figure out the other by figuring out how they add up to 100. If you got three things, clearly you know the first two, right? If they add up to 95%, the last one's got to be 5% because they all add up to 100, blah, 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 blah. So let's go ahead and take it to our chlorine here, and let's go ahead and start a new slide. Okay, so I just made a new slide there and just kind of rewrote that information out. By the way, sometimes these percentages are called relative abundances, and they do vary a little bit around the world and around the universe, actually, but we'll just go ahead and pretend that they're just a fixed number. So let's go ahead and multiply things up. So we have the chlorine 35, so that is, oh wait, I said we start with a percentage, so 75%, got to remember that 75 over 100 times by the mass, so that's 35U, plus 25%, okay, times by the mass, that's 37U. And if you add all this up, actually, you should get 35.5 atomic mass units. And if you're kind of wondering, did we do it right? The answer is yes, we did. But how could you tell we did it right without actually just repeating the math again? Well, we know if it's an average of two things, one is 35 and one is 37, the average has to be somewhere between the two, right? It can't be lighter than the lightest, it can't be heavier than the heaviest, it's got to lay in between. We also know if it was 50-50, it would lie exactly halfway in between. So if it was half of one and half of the other isotope, it would be exactly halfway, which is 36. Because it is 3/4 chlorine 35, almost said 37, sorry, it's 3/4 or 75% of the lighter one, it's going to lay on average a little bit closer. So you can imagine, right? So if we draw sort of a number line here, and here's 37, and here's 35, apologize for my sloppy writing, since 3/4 of the atoms are the lighter one, the mass is going to be kind of 3/4 of the way in between, and so that would be 35.5 AMU. So that is how you calculate average masses, or atomic weights, or whatever you want to call them. That's the name of the game. So let me give you another example to try. But before I do that, I should probably tie back ground to something we looked at earlier. On the periodic table, if you look at chlorine, right, chlorine's got the symbol Cl, so hopefully you've memorized those element names and symbols. Directly above it, it's got that atomic number, the number of protons. And if you noticed underneath, it actually has a fractional number, and depending on how many digits, it might say something like 35.5. And what is that number at the bottom? That is the atomic mass. So that is the average the average mass, I don't know where WAS came from, the average mass of all the masses of the isotopes present. And of course, that was your atomic number up top. So every atom on the periodic table has an atomic mass listed for you. So we've done the math for you, although, where does it come from? It's kind of fun to try. So let's try another example, and we'll just kind of do a polls, and you can work it, and then I'll show you the answer. So let's go to another slide. Okay, so copper is present in two different isotopes, and 69% is copper 63, and so the remaining, so that would be 31%, is copper 65. So I'm writing it a little bit differently before, but I'm just getting a little bit lazy. So we can figure out the, and actually I should probably put that like 69.0 and 31.0 just to give us a little more precision. So we can take that information and we can find the atomic mass. So this would be a good point where you should pause the video and have a go and see what you come up with, and then we'll compare notes. So go ahead and hit pause and try it, and then we'll go through it together. Okay, are you back? So probably the first thing we need to do is we need to figure out the mass of copper 63. And again, we are just going to pretend that this weighs 63 and the other one weighs 65 atomic mass units, just because, it's easier just to assume that protons and neutrons have a mass of 1U, and for more precise work, we can't really do that. But okay, so here we go. 69% of it's copper 63, so almost 3/4 of it is copper 63. So just like before, we would expect the average mass to be closer to 63 than 65. And the recipe basically just says take the percentage, and so divide by 100, that's a percent, and multiply by the mass of each isotope, so 69 over 100 times 63 atomic mass units, and then 31 over 100 times by 65 atomic mass units, and that gives us the weighted average. So I'm going to go ahead and clickety-clack and take my calculator, my trusty calculator, so 69% times 63 plus 31% times by 65 is 63.62. We'll just say 63.6 for this one. So we've played a little bit loose and fast with the significant figures here, but I hope you forgive me. And if we go ahead and we look at the periodic table and we say, well, how close were we? Copper is somewhere in the middle of the periodic table. It is element 29. Okay, so that's the atomic number. And underneath, I've got a little itty-bitty tiny pocket periodic table. My periodic table says 63.55. So the average mass of all the isotopes is 63.55. And we can see this agrees very nicely with what we just calculated. So if you got that number, congratulations, well done, you're a superstar. If not, work through it again and just see if you can't come up with it a second time. All right, now for something completely different.